Hi class, welcome back. Today we're gonna continue with chapter 1 and specific 1.3. This section will discuss a different approach of evaluating limits. This is known as the analytically approach. Last time we talked about the graphing approach and numerically approach, and that is by looking at the graph or creating a table. So this approach is actually more direct, more practical. It's the one that I mentioned last time. That is the way we're gonna most of the time approach a limit. So the objectives for this section will be to evaluate a limit using properties of limits, which we'll define pretty soon. Develop and use a strategy for finding limits. Evaluate a limit using dividing out technique, and then evaluate a limit using the rationalizing technique, and then evaluate a limit using the squeeze theorem. Um, so let's begin with the first one. So in previous approaches, in the last section, we defined that the limit of f of x as x approaches c actually does not depend on the value of f at x equals c, right? So, but it happens to be that if the limit is precisely f of c, then in those cases we can find the limit by evaluating by using direct substitution. That is, that if the f of x, if the limit of f of x as x approaches c equals f of c, in such behavior, we'll call that the function is continuous c. So what I'm trying to say here is that we will use the following three basic limit properties to redefine the way of finding the limit. The first one the first one is if we're finding a limit of a function that happens to be a constant. That means like this right here. If you're looking for the limit of 3 as x approaches 2. So what happens here, and I'll do this graph here. If I have a graph, right, and the function happens to be 3, that means f of x is equal to 3. That means that for every value of x, right, every value of x, the value of the function is always 3. It's always 3. So maybe I'll write here one more thing. Say this is 3, this is 4, this is 5, this is your y value, this is your x values, right? So it doesn't matter what x value you have, this would always be 3. So in this case, right, it kind of makes sense now that as x approaches 2, right, the value is 3. So because the value of the function does not change, right? It's always 3, it's always 3, it's always 3, no matter for what value of x is. So in other words, if the limit of if you're looking for the limit of a constant, it actually won't depend on this value anymore, because it's a constant. It's always going to be 3. That's what this is saying. The other one that we have here now is in the case that we have an actual function of x. So here we go. We have a function. Let's say this function is 2x. And so I'm going to go ahead and write a few things here. It will be 1, 1, 2. So that will be, the graph will look like this. Something like this. So what we're saying here is x approaches -4, right? What is the value of the function equal to? Well, it's going to, oh, sorry, and then I did this wrong one. So let me try again here. Sorry. Sorry. So let me try this again. Actually, I drew the wrong one. All right, so if we have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, so this is the function supposed to be f of x equals x. All right, so f of x equals x. And so if we notice here, as x approaches negative 4, negative 1, negative 2, negative 3, negative 4, the value of the function should be negative 4. Should be negative 4. So what we're saying here is that all we gotta do here is do a direct substitution of this. So what happens here is if you have an x value, all you gotta do is do a direct substitution of x in here. And if you notice, the same thing happens here. If we have a power, all we're going to do is we're going to do a direct substitution just like we're doing here. And that will give us the limit. All right. So that's the new basic way to find the limit is just do a direct substitution. And we extend these properties with the next 5 properties. The next one is a scalar multiple, and the other one extends to the plus or minus of 2 functions, and the product of 2 functions, and division of 2 functions, and the power of 2 functions. And basically what we're saying here, what we're summarizing, is that the way we're going to approach the limit is by plugging in these numbers, plugging this number, right? X equals 2, we're going to use direct substitution. Direct substitution. That means x equals 2, and then plug it into the limit. So we'll have the limit of 4x squared plus 3 as x approaches 2 equals to 4 times x plus 3. So what we're going to do here is this is going to be a direct substitution, and what we're going to have here is by using following order of operation, what goes first? Power. So that'll be 4 times 4. Then the product, so that's 16 plus 3, and then the sum. So that's 19. And there you go. So in conclusion, what we have here is that the limit of 4x squared plus 3 as x approaches 2 is going to be 19. And so that's what we're saying here is you're using just a direct substitution. And so let's try. Now, this works because if you notice, we're able to get an actual number, right? We're able to actually get a number. We'll see a case where we don't get something like that. Not right now, but in a few examples. So the next one is talking about the limit of a polynomial and a rational function. So in general, what we're saying here is that this will be true. You can use a direct substitution anytime you're dealing with a polynomial, such as this case this is a polynomial. Remember what is a polynomial? A polynomial is any function where you have, powers. Let me do a little more variety. 3x minus 1. So as long as those powers of the x's happen to be whole numbers, then that means that this whole thing will be a polynomial. So if you have a negative number, then if you have a fraction, then that's not a polynomial. So what we're going to do is we're going to do a direct substitution in here when we're dealing with a polynomial. We are sure that that's going to work out. And it's also going to work out when you have a division. You're going to do a direct substitution as well, but you're going to be careful to make sure that this does not equal 0, right? So that's the only problem that we will have. So let's try this one here. So what we're going to do, we're going to do direct substitution. Direct substitution, right? We're going to try that. So let's go ahead and do that. So it'll be the limit as x goes to 1, x squared plus x plus 2 over x plus 1. And the limit of this will be, we're going to do a direct substitution. Wherever we see an x, it's going to be replaced with 1, 1, 1, right? And thus we end up getting 1 plus 1 plus 2 over 1 plus 1. And following order operation, first we add all the numbers on the numerator. It will give us a 4, and add the denominators the denominator, so that'll give us a 2. 4 over 2 is 2. And so there you go, right? We actually get a number, right? We end up getting an actual number. So the limit does exist for this. So the limit of this function, of this quotient, of this rational function is going to be 2. And if you notice, we didn't have to use a table. We didn't have to graph this. We can just do a direct substitution. And that's what we are want you guys to do, right? We want you to do that. That's actually how you're going to start your process of finding the limit. And this process will extend also to radical expressions. We're going to do that to radical expressions. So that's what we're saying here, that this will be extended to radical expressions as long as, and it's going to be fine as long as the index of the radical is an odd number. You can plug in anything you want. We're actually going to be careful if your index of the radical is even, then in that case you can only plug in positive values because otherwise it will be undefined. And the next theorem follows the radical theorem, and the other one is as known as composition. The composition form is that we will follow in order. When we have a function inside a function, as we see here, a g of x is inside of f, what we're going to do is also a direct substitution, but first it's going to go through the g. Then the output of g will be the input of f. And we can kind of see that in this example, right? You first evaluate the limit of the inside function, followed by the output of this, which will be probably something like L, and then output, and then the evaluate that value. So here's the next example here. So let's try A. So the limit of the square root of x squared plus 4 as x goes to 0. Then we got to be careful. What we're going to do is we're going to plug in the 0. We're going to use direct substitution. Direct substitution. So we're going to have the square root of x squared plus 4. So that would be x equals 0, right? And we're going to finish by evaluating it. So it'll be the square root of 0 squared is 0 plus 4 is 4, which equals 2. So what we're saying is the limit of the square root of x squared plus 4 as x goes to 0 is 2. All right, next one, same thing. We're going to apply the same concept. And then we're gonna evaluate it. So the limit of the cube root of 2x squared plus minus 10 as x approaches 3. We'll use a direct substitution. So we have the cube root of 2 times x squared minus 10. And so we end up getting the cube root of 2 times, and following order operation will be times 8 minus 10. Be careful that radical needs to go all the way. So we have the cube root of 2 times 8 is 16 minus 10, right? Following order operation, which will give us the cube root of 6. And that will be... Oh, sorry, did I make a silly mistake here? I did. It's supposed to be 9. Right? That's a 9. So 2 times 9 is 18. There you go. And then this will be 8. And then the cube root of 8 is 2. And so, in conclusion, the cube root of the quantity 2x squared minus 10 as x approaches 3 is 2. Now, I want to make sure that since we have done already a few examples like this, I want to point out that as I mentioned at the beginning of the semester, it's very important that you follow proper notation. So you must write down the limit notation here. Once you do the direct substitution, then you no longer put the limit, right? You're no longer allowed to put the limit. Once you apply the direct substitution, then that's gone, right? Now you only have this. But if you haven't done it, if you haven't applied the direct substitution, then you must carry the limit notation. As you guys will see in the next example, not this example, but coming up. So here's another example of we can apply direct substitution, and these are the trigonometric functions such as sine, cosine, tangent, cotangent, secant, and cosecant. So here we go. First one, let's apply the limit of the tangent of x as x goes to 0. So what are we going to do? We're going to do direct substitution. So that will be tangent of 0. What is the tangent of 0? Tangent of 0 is 0. So the limit of tangent of x as x approaches 0 is 0. So far good. We'll try the next one. The limit as x, the limit of x times cosine of x as x approaches pi. Again, we're going to use a direct substitution. So we're going to have pi times cosine of pi. And this will give us pi, and cosine of pi happens to be -1. And so we end up getting negative pi. So the limit of x times cosine of x as x goes to pi is negative pi. All right, and so that looks good. The next one, again, we'll apply the direct substitution. We're going to start always with that. So direct substitution. And this will be replace x with 0, right? And I've been doing this of writing those numbers in red. So I'm going to just sort of remind you that there was that was being done, right? All right, so that way you guys can see that I've been doing this direct substitution. All right, so then we end up getting sine square of 0. This is the same thing as sine of 0 square. What is sine of 0? Sine of 0 is 0. And then you square that, and that gives you 0. So the limit of sine square of x as x goes to 0 is 0. There you go. So far we have found the limit of this by using direct substitution. There was no issue whatsoever of what to find, what the limit was. Okay, so we're moving on to the next part where we actually start to get a little more complex, and we have to kind of think about a different strategy to find the limit. So a different approach is to, and again, we're going to continue to try to plug in and do direct substitution, but we're going to find out, right, as we're going to see here, we're going to apply the direct substitution, and you will see that there is a problem. So let's do that. This is how I expect you guys to be able to do it. So you will do the limit of x cubed minus 1 over x minus 1 as x approaches 1. So as you do the direct substitution, you're going to have cubed minus 1, x minus 1. Direct substitution, that's a 1, that's a 1. The problem with this is that 1 cubed is 1, and so we end up getting 1 minus 1. And then the bottom, we also get 1 minus 1, which is 0 over 0. This is a problem, but a nice problem to have, because actually this gives us a hint. This gives us a hint. This actually tells us something. This actually tells that that we can approach this in a particular way. We can actually work. We have to go back again and retry the problem with a different strategy, and the strategy would be to apply sum algebra. And the concept of that will be I'll explain that in a second. But the way we're going to approach this is by try to simplify this. How do we simplify it? Well, this is where we start using some of the algebra that we have learned in the previous semesters. So think about how we can simplify a function over a function, right? How can we simplify an expression over expression? Well, by factoring and cancel any common factors. How do we cancel? How do we factor x cubed minus 1? Well, there is a way where we can simplify x minus 1 by factoring an x minus 1, right? We can factor x cubed minus 1 by factoring x minus 1. And what's left behind by different approaches that we have used in previous algebra courses is that we're going to be left with x squared plus x plus 1. So this is what we're left with, and what we remember in algebra is that these can cancel each other out. So what we have here is that the conclusion is that the limit of the original problem happens to be the same as the limit of our new problem. Let me write it out. So what we're saying is that if you want to find the limit of the original problem, it's equivalent to finding the limit of this new problem. These two problems have the same limit. And so let me drag you guys to the side of the picture so you can see what I mean by that. This is the original function. And the original function, if you notice, when you plug in x equals 1, you end up getting a 0 over 0. That's what that means. Right here. 0 over 0 gave us this whole. But once you simplify that, that gave you a different function. They're not the same. They're not the same functions, but they're very similar. How similar? As similar to every extent of the function except at that point. At that point, they're different. Right here and right there. Right? They're identical to each other except at that point. Right? But nonetheless, they're different functions that behave the same way. They are different and only by one single point, but the limit happens to be the same. The limit of them happens to be the same. Because remember, in order for us to have a limit, you don't actually have to have the number there, right? So they have the same limit, and so therefore we can, if we can find the limit of this function, then we have found the limit of this function. So let's try this again by using direct substitution. So this will be 1 squared plus 1 plus 1. So that will give us 3. So the limit of x cubed minus 1 over x minus 1 as x approaches 1 is 3. There you go, right? We found it. And so this was done by using a function that was it agree at all points but 1, right? This is by simplifying. By simplifying, it required us to use some factorization and cancel some values. Now this happens to be the second most popular approach to find the limit. We already know that the most popular way to do it is by using direct substitution, right? And most of the time it would work. The second thing to do is to try to cancel by simplifying, which we know we do that by factoring, and then we try to cancel those common factors. Now, a hint, here's a cool hint for you guys. A hint here is that if you end up getting 0 over 0 when you plug in x equals 1, this means that the numerator and the denominator share a common factor. Because of that, they both share a common factor. So it was actually very easy to know what was the factor, one of the factors of the numerator. Sometimes students have so much trouble figuring this factorization. Not for the for those who have done this more often, because we all know that if this is true, then the x minus 1 has to be a factor on the numerator. The x minus 1 has to be a factor on the numerator. So what I do often is I factor the x minus 1 because I know it has to be, and then I try to argue what's the other factor. So you guys see, I know half of my work. I hope that kind of makes sense. And now you will see me doing those techniques a few times. So here's a quick summary of the strategy we'll be doing. So a strategy to finding the limits will start by first learning how to recognize which limits we can evaluate by direct substitution, which we should try every single time, right? Then we'll, when the limit of f of x as x approaches c cannot be evaluated by direct substitution, then we'll try to find a function g that agrees with f at all values of x other than x equals c. Choose that g such that the g of x can be evaluated by direct substitution, and then conclude it by using direct substitution. If those do not work, then we go back to the least popular way, which is graphing a table, right? Graph or using a table, right? Again, those are the most basic ones. Those will guarantee to always work, right, by making a table, but it's too time consuming, right? Okay, so let's try another one. The next one is similar to what we just did. It's by using the dividing out technique that we just discussed. So we'll do the same thing. We'll do a direct substitution. So here we go. The limit as of x squared plus x minus 6 all over x plus 3. We'll do a direct substitution. Minus 3, minus 3, minus 3. Right? And then let's see what we get. Minus 3 square, the quantity of minus 3 square is 9. Minus 3, minus 6, minus 3, minus 3, and we end up getting 0 over 0. Again, this is a problem, but it also gives us a hint. It means that we can try this again. We can try this again, but we need to simplify. In other words, divide and cancel, right? So let's try this again. Try again. So the limit as x approaches negative 3 for x squared plus x minus 6 over x plus 3. So that means we're going to have to simplify this before we do direct substitution again. And if you notice, I am writing the limit because as we did before, notice that I simplify. I have to carry the limit. If you don't, I'll take off points, right? Because you're not writing proper notation. It's not consistent. It's not an equation. It's not an equal sign. So please make sure you know when to write the limit and when you don't. We talked about that a few times. You will remove the limit notation once you apply the direct substitution. So we're not doing that. We're just doing some algebra. So what I know about this is that we end up getting 0 over 0, which means that the numerator must have a factor that is x plus 3. It must have it. So now that I know that this is x plus 3, I can figure out what's the other one. So factoring a trinomial means is a factorization of two binomials, which means it'll be, by guess, right? It'll be x minus 2, right? X minus 2 times x plus 3 will give me x squared plus x minus 6. So now we'll cancel those two, and the limit of this, maybe I'll write it here, the limit of x minus 2 as x approaches negative 3 is going to be, by direct substitution, negative 3 minus 2, which is negative 5. So that means that the limit as x approaches negative 3 of x squared plus x minus 6 all over x plus 3 is negative 5. Right? We're not saying that these two are the same, right? We're not saying that these two functions are the same. They just behave the same way. They're everything the same except by one number. And there you go, right? We found the value. So here we use direct substitution. So quick recap. We did at the beginning direct substitution, and we end up getting 0 over 0. That gave us a hint and meant that we had to go back to our notes and try to simplify the original function. And we did that by factoring and canceling common factors. Once we had the simplified version of it, then we did the direct substitution, and we no longer have to put the limit anymore, because we have applied the limit, and so that gave us negative 5, and so we have our limit. All right, moving on to the next part, the rationalizing technique. This is a technique that we have learned in pre-calc, and it's known as rationalizing the denominator or rationalizing the numerator, right? So here we go. So another way to find the limit analytically is to rationalize using that rationalizing technique, which involves rationalizing the numerator of a fractional expression. Recall that rationalizing the numerator means multiplying the numerator and the denominator by the conjugate of the numerator. For instance, to rationalize the numerator of the quotient square root of x plus 4 over x, we would need to multiply the numerator and the denominator by the conjugate of the square root of x plus 4, which is the same thing but with the different sign in the middle, right? So it would be the square root of x minus 4. So if we want to apply this limit, we would do the same thing, right? We would try to direct substitution. And I can probably already recognize that this is not going to work. But again, right now, you are still trying to develop this skill, so you may have to actually do it, right? So once you apply, you will have to do direct substitution, and once you apply that, then you can drop the limit notation. So 0, 0, and this will be the square root of 1 minus 1 over 0, which is 1 minus 1 over 0, which is 0 over 0. Again, this tells us something, right? This gives us a hint that we need to try this again, right? We try this again. So try this again, but this means we'll have to do some algebra along the way. So the limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. What we're going to do is we're going to rationalize the numerator. Which means multiply the numerator by its conjugate. The conjugate of this is the same thing, except change the sign minus to a plus. Multiply both the numerator and the denominator by the conjugate. Now remember what happens when you multiply by the conjugate. Let me write that over here. When you multiply by a number by its conjugate, what you end up getting is the difference of squares. That's from algebra. So what we end up getting is basically going to be the limit of the difference of squares. Now, please leave the product of the denominator as it is, right? Do not distribute the x, right? Remember something in particular, right? That when you have a fraction bar, fraction bars are a form of grouping. So even though you don't see parentheses there, they're there. Same thing here, right? There's a fraction bar, so that's grouping those two together. And that's grouping those two together. So technically, when you multiply these two, you wouldn't multiply that by that and that by that. But I like it again. Do not do that. Just leave it as it is because you don't need it. So you're making your life harder than it is. So just leave it as it is. It's just it's not needed to make that much work. What you're focusing is on the numerator, and what happens here is that you're multiplying this with that, and then this with that, and then this with that, and this with that, which is pretty much the difference of squares. So this will be the square root of x plus 1 minus 1 square. And this will give us the limit of x plus 1 minus 1 over x times the quantity of x plus 1 plus 1 as x goes to 0. Now, if you notice what happened here is that the square root and the square cancel each other out. That's how you end up getting x plus 1. 1 square is 1. Now, please note that because x plus 1 came from a group of the square root and the square, right? Then it stays as a group. Now, that's the logic behind the algebra, but there's nothing in front of it, so if we drop them, it wouldn't be an issue. In fact, we're actually going to do that because those two are going to cancel each other out. So we end up getting the limit of x over x times the square root of x plus 1 as x goes to 0. Now, if you notice here, we mentioned that 1 plus 1 and minus 1 will cancel each other out. But even more, you notice that if I could technically picture this as being multiplied by a 1, right? There's always a multiplication of 1. The reason why I'm doing that is because those would cancel each other out. And I want to make sure that you see that there's always a 1 left as a product. And so if you notice that x is gone, and you should check that from here. When we did that, the fact that x was an issue, you expect to remove that x. You expect to remove that x when you're doing this process because that was the issue. If this would have been x minus 1, then you should expect to get rid of that x minus 1, right? One way or another. All right, so now let's do the direct substitution. So this will be 1 over the square root of 0 plus 1 plus 1. And that's going to be 1 over 2. And so therefore, the limit of this function is 1/2. And there you go, right? We can verify the same result by making a table or graphing it. We would have seen that, in fact, that as x goes to 0 from both directions, the value of the function is approaching y equals 1/2. Y equals 1/2. Okay. And then lastly, we'll talk about the squeeze theorem. Squeeze theorem is a big theorem, but we're not using it as much in this class. You will use it more later on. But the concept is this, that if you're trying to figure out the limit of this function, right, at x equals c, right, what you can do is, if this is maybe too abstract to figure out, what you can do is you can use something that you probably are more familiar with, like g and h. So let's pretend that g and h are two functions that you know how to find the limit of. As we've seen here, there are some cases where the limit is too hard to find, right? Where you have to do more work to find them. But what we're saying here is that if that's the case, if f is a hard function to find, but you know a beautiful function h and a beautiful function g, that you know how to find the limit, and you know that f is always in between h and g, then when you approach, when you try to find the limit of as x approaches c, well, we know that the h and g are squeezing the function f, right? Then that it will force, force for us to be able to actually find the limit of f at there, and that's what the squeeze theorem is saying. And the squeeze theorem was used to find these two results, and this is very important. This is very important. We want to memorize these two theorems. You should know them by heart. They're very important. So we'll keep those in mind throughout the entire semester and in the future as well. Squeeze theorem, you will see those that property more later on. But right now, this is what I want you to focus from the squeeze theorem. So let's go ahead and find the limit of and if you notice, the important thing about this is that as x approaches 0, right, you end up getting a 0, right? If you find this one here, you have the limit as x approaches 0 of sine of x over x. And if you use direct substitution, you end up getting sine of 0 over 0. And we know that this is 0 over 0, right? This is a particular important result, but there's no algebra that we can use to get to actually find this limit, right? There's no way we can simplify this using basic algebra. So the squeeze theorem actually helped us be able to find the limit. So there is a lot of work behind the scenes that help us actually find this value of 1. Same thing with this approach, right? We have minus 1 minus cosine of x over x. If you're plugging a 0 there and a 0 there, you end up getting 0 over 0. But by using the squeeze theorem, we were able to conclude that this is in fact actually 0. So there's a lot of squeeze theorem. The squeeze theorem is very important behind the scenes in those two solutions. All right, anyway, so let's move on to the next one. The limit of tangent of x over x as x approaches 0. So we have, by direct substitution, tangent of 0 and 0 over 0, which is 0 over 0. Again, this is a problem, but it also gives us a hint, right? Now, we don't have a special formula like this to like that for the tangent, but we can actually we use one of those two to actually take advantage of and find the limit of this. So let's try this again. So we don't have any algebra we can do that, and we don't have any special trig limits that will help us with this. So instead, what we're going to do is we're going to go ahead and use one of those two. In fact, what do we know about tangent? Tangent is, by definition, sine of x over cosine of x. And this x is this x over here. So what we're going to do here is I'm going to do some algebra and rewrite this as sine of x over cosine of x times 1 over x, right? So you can change a division into a multiplication by using the reciprocal, right? Do you guys remember that? This over this, what happens? You will have this over the reciprocal of this, right? times the reciprocal of this. Reciprocal of this means that you flip those two. That's from algebra. All right, anyway, so we're going to separate those two, the limit of sine of x, and switch those two. That way we can have it like this. And now we know what the limit of this is. We know the limit of this is going to be 1. And we know what the limit of this is going to be positive 1, right? So the limit of these two actually exist. So we can actually separate them, right? That's the reason why we can do this. The limit of sine of x over x as x approaches 0 times the limit of 1 over cosine of x as x approaches 0, right? By the special trig limit theorem over here, this is equal to 1, and this is equal to 1 over 1, right? By using direct substitution. So this gives us 1. Now, we can do this because we know, this is very important, we can do this separation. Very, very important, is that we can do the separation from here to here because we know that the limit of this exists and the limit of this exists. This is the reason behind going back up here. We are allowed to separate the two products as long as we know that the limit of this exists and the limit of this exists at x equals c. So it's a very important component. And so there you go. We were able to find the limit of the tangent of x over x. So very important property. It's very important because for the major, when we're finding the limit of a function, we can often use the algebra to simplify it. But for trigs, it's very hard to do some basic algebra, right? We would have to use some hard algebra to be able to work those out. So these two are sort of like the gate way, right? These will allow us to get around that heavy, probably heavy algebra. So these are very important. So keep those in mind. Those will be very important for the test. So I hope you guys find this helpful. Let me know if you have any questions, and I'll see you. I'll catch up with you guys next time.